All right, well, it's 5:10. I think that's the best segue we'll get into redox. All right.
Whoops.
All right, can everybody see my screen all right?
Yes.
Yep.
Can everybody hear me okay?
Yes.
Yep.
And if everybody could mute yourself while we do the lectures, that would be great. So I'm going to do a quick introduction just into the basics of redox so we can get kind of a good foundation laid. And then we're going to throw it over to Chris and he'll give his lecture. And then my actual lecture will follow that. So we're going to start our basic introduction to redox, which is reduction and oxidation. So a really good way to remember redox is this simple word, oil rig. Oxidation is loss, reduction is gain. And it's loss and gain of what? Electrons. It's really not that complicated. The oxidation of something like iron will result in the iron losing electrons. Oxidation is loss. The iron was oxidized, it lost electrons. Reduction is something gaining electrons. So this is where it gets kind of confusing for a lot of people because gaining something is called reduction, which it always throws people off. Just remember reduction is gain. Gaining electrons is reduction. What's being reduced? The oxidation state. So the oxidation number is being reduced. So it's going from, either 0 to a negative or +3 to +2. That's a reduction. So it's easy as long as you remember oil rig. So if we look at our little example here, we have iron and we have oxygen gas, O2. And so that is transferring, the iron is transferring 2 electrons to the oxygen. So it's going from 0 to +2. It lost 2 negative things and became positive with an equal charge. So it lost 2 electrons and became +2, iron +2 or iron 2. And then oxygen, which was neutral, gained 2 electrons from the iron and it became -2. It gained 2 negative things and became -2 negative. And so this doesn't just happen with metals. We also can see here on the right, our product over here, NH3, is ammonia. So we can see hydrogen and nitrogen. So here, the hydrogen is actually the one that is transferring electrons to the nitrogen. So nitrogen is going from a neutral 0 to -3. It gained 3 electrons, so -3. Hydrogen is going from 0 to +1. Each one of those hydrogens lost 1 electron, so it became positive. So it's not too bad. Just remember oil rig. So one process that is really influenced by oxidation or reduction is one of my favorite art styles, which is black figure pottery. It's really phenomenal. And the fact that they figured this out in 700, 600 BC is just phenomenal. So we can look at the first step of this, which is oxidation. This is a 3-phase firing process. It goes oxidation, reduction, and reoxidation, not redox, but reoxidation for your third step. So in this first step, you take your pot and you put it into a kiln. And what you're going to do is convert all of your different iron oxides, iron hydroxides, and different compounds that are in your clay and also in your paint that you, well, not paint, but slip that you applied to this. You're going to convert all of that to an orange-red iron oxide, Fe2O3. So you're going from iron, you're adding oxygen and heat, and creating Fe2O3. So it's all converting to Fe2O3 in the first step. So this is done inside of the kiln with plenty of oxygen and at about 800 Celsius or so. That's generally the figure given. So it has plenty of access to oxygen in the atmosphere, so it is able to reduce. So oxygen, you can see, is gaining 2 electrons from the iron, which is donating 3. So in the next step, we're going to reduce it. So when we reduce this in the next step, all that Fe2O3 is going to convert to iron 2 oxide, which is a matte black color. And so when you convert that, you also have on your pot a type of slip, which is going to crystallize, it's going to fuse together, and that actual black slip is going to give you this black color here that creates magnetite. So that melts together and fuses at about 975 degrees. So you can see again, here is our simple reduction and oxidation scheme. So here the iron is going from +3 to +2. It gained an electron, it gained 1 negative electron. So 3 plus -1 is +2. So that is our reduction of the iron. Its oxidation number +3 was reduced to +2. And then our oxygen over here, it stayed the same, stayed -2. But over here on the right side, we can see that carbon went to +4. So it from +2 to +4. So it actually lost 2 electrons and became +4. So that's our reduction step here. And the final step, it's reoxidation. So that last step, which was, actually, let's go back really quick and we'll explain this just because it's so cool. I wouldn't normally go into this, but it's just amazing. What they would do is take a bunch of leaves and branches and cover up the ports of the kiln, and it would create a smoky reducing environment filled with carbon monoxide as opposed to CO2. So that carbon monoxide, that reducing smoky atmosphere is actually what drives this reaction forward. And they raise that temperature from 800 to 975 degrees Celsius. So then in the final step, the reoxidation, they unblock those ports. They let oxygen flow back in, so it's no longer a smoky reducing environment. It's back to an oxidizing environment. So you can see here that the iron oxide that we had produced in the last step is going to reoxidize to Fe2O3, similar to our first step. And that's going to convert the matte black back to this orange background that we see. So this black color that we see was the magnetite that was produced in the oxidation step by the fusion of the slip that was applied to the pot. The orange is the Fe2O3 that we convert it back to. So when we look at this slide, we can actually see what that whole process looks like. So here is how the pot would have went into the kiln. We would have oxidized the pot and created a bunch of Fe2O3. Then we would have reduced it to this matte black. So the entire pot reduces to matte black, and that fused portion, that slip, stays fused and stays black because oxygen can't reach those fused areas. So it's kind of like a glaze on a ceramic. It's very similar to that. So then in the last step, it reoxidizes. So everything that wasn't sealed with that slip turns back to Fe2O3. So that's our 3-phase oxidation, reduction, reoxidation. So we can see the transfer of the electrons is really not that complex. We're losing 2, we're gaining 2, we're losing 1, we're gaining 1. It's really not that bad. So where people normally get confused, though, is transferring from what's called, it's usually called pure redox, what we were just looking at, where we have pure elements transferring electrons, and it's very nice and clean when you look at it on paper. In organic redox, a lot of different things can occur and it becomes muddied. So really in organic redox, it's not that different. We don't necessarily need to transfer electrons. We can share electrons in covalent bonds and things like that. But organic oxidation is actually really simple to remember. If something gains bonds to oxygen, it's been oxidized. So oxygen is a really good oxidizing agent. You can also use halides or halogens to oxidize things. So when carbon or any other element gains a bond to oxygen or a halogen and loses a hydrogen, for example, it'll have been oxidized and its oxidation number increases. When something is reduced in an organic redox reaction, generally we're looking at the gain of hydrogen and a loss of a bond to oxygen. So if something loses a bond to oxygen and gains a hydrogen, or just loses a bond to oxygen, or just gains a hydrogen, it's been reduced. And so that's really the fundamental difference between those two different schemes of pure redox and organic redox. So in organic redox, all we really have to remember is that if we're gaining bonds to oxygen, we're oxidizing. If we're losing bonds to oxygen, we're reducing. And so now we're going to toss it over to Chris. Now that we have a decent fundamental understanding of how the electrons are being transferred back and forth. And so Chris is going to go into his cellulose lecture.
So I assume everyone can hear me and everything. Last week, our topic was ethanol. So starting with really simple oxidation reduction, if we take ethanol and light a match to it, make a flambe, we get fire, and we reduce that ethanol, or I'm sorry, we oxidize ethanol to carbon dioxide and water. We see the same kind of reaction with rust. 4 irons plus 3 oxygens goes to 2 Fe2O3s. And again, as Luke was saying, we have the iron going from iron 0 to iron 3 for those 12 electrons. We have 3 oxygens going from from 0 to -2 with 12 electrons, so it balances out. And again, remember, oil and rig, oxidation is loss of electrons, reduction is gain of electrons. So we usually think of oxidation as a slow process, a lot like watching paint dry. And oil paint dries by oxidation and cross-linking. And we know that can take up to 100 years for the oil paint to fully cure. But oxidation can be surprisingly quick. Remember oily rags, if you've been working with drying oils, they can spontaneously combust from the oxidation of the oil on the rag with oxygen in the air and cause a fire. So we always are very careful with our greasy rags. We think of rusting as being a slow process. Was going to show lighting some fine steel wool on fire, but it turns out I threw out my fine steel wool, so no pyrotechnics today. But there is pyrophoric iron, where the iron can oxidize to essentially rust very quickly, very exothermically, and very dangerously. Probably everyone knows about cannonballs being recovered from the ocean, where the iron and chloride get together and make that pyrophoric iron in the middle. So tarnish is the oxidation of silver by sulfur-containing materials. Again, nothing new. So we have 2 silver molecules silver atoms in the ground state. And we'll just say hydrogen sulfide, although any sulfur-bearing material can generate the sulfur in the air we know wools can cause corrosion of tarnishing of silver. And that goes to silver 2 sulfide. So we have the silver going to silver plus, hydrogen going to gaining 2 electrons and going to hydrogen gas. The important thing here is that silver sulfide has an incredibly high solubility constant, so 8 × 10⁻51. EDTA's chelating power with silver is 5 × 10⁻8. So if we wanted to remove silver sulfide with a chelating agent, it's never going to happen, because the difference between the -51 being so insoluble and the silver EDTA being comparatively weak, we're never going to get silver sulfide to chelate and the silver go into EDTA. So what we can do is use reduction and put our silver in a pot of water with, I typically use sodium bicarbonate, attach a wire or just have the aluminum foil in contact with the silver, and we have an electrochemical reaction happen where we bring the silver back down to its metallic state and sulfide the aluminum. So we have the reduction of the silver plus to silver 0, and the oxidation of the aluminum to aluminum +3. And you notice we have our electrons flowing through the wire here, and slowly our black tarnish is reduced back to metallic silver. So as Luke was saying, organic oxidation reduction is different. It's really kind of the same, but confusing to look at in terms of moving of electrons. So as Luke said, oxidation is the increase of oxygen or decrease of hydrogen atoms and bonds. Reduction is the decrease of oxygen or increase of hydrogen atoms or bonds. So let's look at ethanol again. If we have ethanol in our body and it goes into our liver and is processed by alcohol dehydrogenase, we get an aldehyde, acetaldehyde, and that's what gives us hangovers, headaches, feeling rotten, throwing up, all that sort of thing. Not in the liver. If we take that acetaldehyde and react it with potassium dichromate, we oxidize that acetaldehyde to acetic acid or a carboxylic acid. So we can look at something like isopropanol, a secondary alcohol, and oxidize it with potassium dichromate again, and we get acetone, a ketone. And we can't go any further with the oxidation. We can't bring that to a carboxylic acid because we've used up all the valence sites on that carbon atom, all 4. So the 1, 2, 3, 4. And you can see that this is oxidation because we go from 1 oxygen bond between the C and the O to a double bond. So we've increased the number of bonds to oxygen, even though the number of oxygens hasn't changed. We can also reduce these materials. So if we take acetone and react it with sodium borohydride, we can go back to isopropanol. So we're going from a double bond, 2 bonds to oxygen, to a single bond to oxygen. So we've reduced the number of oxygens. We can use sodium borohydride to take an aldehyde and reduce it to a primary alcohol. Again, a double bond to a single bond, so a loss of a bond to an oxygen. And we see that sodium borohydride is a very versatile reducing agent. We can even think about it as a reducing bleach. But the sodium borohydride isn't strong enough to take that aldehyde all the way to, isn't strong enough to take a carboxylic acid all the way to a primary alcohol. So it will take care of a ketone or an aldehyde, but it can't reduce a carboxylic acid. So I've been really curious about paper, even though I'm a paintings conservator. So the last couple of weeks I've been doing my best to learn a little bit more about the chemistry of paper conservation. And it's a hell of a subject, so hats off to all you paper conservators. So we can think of paper as a mixture of alpha cellulose or cellulose, which is a linear polysaccharide composed of glucose linked by beta-1,4 glucoside bonds. Hemicellulose, which is a complex branch polysaccharide, which is mostly glucose, but also contains 4 other sugars. And for the time being, we'll ignore lignin because that's just makes my brain hurt. So if we look at a lignin-free paper, it's a mixture of cellulose and hemicellulose. If there's too much cellulose, the paper has reduced tensile strength. And if there's too much hemicellulose, we have low tear strength in the paper. So here's a picture of cellulose. And we see how we count the carbons on the glucose molecule. So 1, 2, 3, 4, 5, and 6. And we have a long chain of glucose with that beta-1,4 linkage. So there are a number of processes that reduce the length of the cellulose, reducing the degree of polymerization, chain scission. There's acid catalyzed hydrolysis, alkaline degradation, but what we're concerned about here today is oxidation. So we can look at that 1,4 link, and if we oxidize that, we can break that chain and go to this structure where we've broken that long cellulose chain, gone to a double bond oxygen here. You see we've added a bunch of oxygens in the process. Whoops. So we go to an OH, double bond oxygen, and an OH on this carbon 4 here. We can also oxidize that number 6 carbon and go to an aldehyde or even all the way to a carboxylic acid. And this is what will make that, that cellulose more water soluble by oxidizing that hydroxide to a carboxylic acid. We can also oxidize at the number 2 and 3 carbons and go to ketones or aldehydes. We can break that bond, further oxidizing. So when we think of discoloration of paper, we have a number of things going on. We have chain shortening, so our cellulose and hemicellulose chains can get shorter from that oxidation of the cellulose. The ends of the cellulose polymers can be chopped off and shortened to shorter polysaccharides, and even down to the point of becoming practically free glucose, which can then oxidize to hemiacetals, which are can be very colored, and that can be some of the degradation product we see. The hemicellulose is oxidized to shorter segments of polysaccharides. And those alcohol groups on the cellulose can be oxidized to aldehyde, ketones, and carboxylic acids. So what happens is the carboxylic acids give water solubility to those components that were insoluble. After all, when they first made the piece of paper, anything water soluble washed out in the formation process. So by chopping those long cellulose chains up into smaller pieces, we've made them more soluble. By oxidizing them to carboxylic acids, we've made them much more soluble, those small pieces. And by adding double bonds, aldehydes and ketones, we are changing the absorption of light from the blue to ultraviolet to blue, and our degradation products are turning yellow. So if we wash our degraded paper or oxidized paper, first thing we're going to do in a neutral or acidic wash is remove those short, most oxidized fragments. If we wash at a higher pH, we'll be deprotonating those carboxylic acids, making them more soluble, and those kind of fragments that were too large to dissolve in neutral or acidic water are now soluble because the carboxylic acid's been deprotonated, and we can wash that material into water. And then the last thing we can do, well, not the last thing, another thing we can do is add a chelating agent. And the calcium ions will bridge between cellulose molecules and hydroxide functional groups on the cellulose chain. So by taking out those calcium ions, we can release those more soluble degradation products and allow them float away from the more intact cellulose chains. So we have bleaches, which we also can call them just oxidizing and reducing agents. The oxidizing bleaches, sodium hypochlorite, Clorox, calcium hypochlorite, chlorine dioxide, hydrogen peroxide. And the reducing bleaches, sodium borohydride, sodium dithionite, sodium thiosulfate, sodium metabisulfite, and sodium sulfite. So if we use oxidative bleaching, and this is really stepping out of my my comfort zone, so kind of fools go where wise men fear to tread. So here I am stepping forward. But so with oxidative bleaching, we're creating more carboxylic acids. We're really beating those cellulose and hemicelluloses with a very strong oxidizing agent with the case of the hypochlorites. By converting everything to carboxylic acids, we're making those molecules more soluble, so they're going to wash out. We'll take out those discoloration products. And also, we're going to be oxidizing further those conjugated double bonds of oxygen in the ketones and aldehydes, and decolorizing the material as we bleach it out. Not sure about this, but I wonder about hydrogen peroxide. It's a much weaker bleach. I think what it does, my feeling is that it breaks the deconjugation, decolorizes the molecules without creating as many carboxylic acids. So it's not degrading the cellulose as much. But it's oxidizing those double bond oxygens further. We're losing the color, we're washing out some material, but I'm wondering if because we're not, if we get color reversion because we're not washing out all that material that's been oxidized. It's not been made soluble, it's just been decolorized. And then that comes back as it ages more. Another thing, speaking way outside of my comfort zone, is light bleaching. And from other research, I found that discolored humic material absorbs blue and UV light and creates hydrogen peroxide. So the interesting thing about light bleaching is that the darker an area is, the more hydrogen peroxide will be generated locally. So it's a selective bleach in that dark areas are bleached more strongly than lighter areas. So reduction bleaching. As a non-paper conservator, this has always struck me as the best thing we can do. What it does is it'll take those aldehydes and ketones, if we use something like if we use one of the reduction bleaches, like sodium borohydride, we're converting those oxidation products, aldehydes and ketones, back to alcohols. Remember, we still can't convert the carboxylic acids back to alcohols, but we can convert, oh, and there's a typo. We can convert aldehydes and ketones to alcohols. By reducing those double bond oxygens, the pi bonds, we are reducing any conjugation. So we're shifting the light absorption back into the UV. We're losing that absorption of blue light, so things aren't yellow anymore. And in a way, it repairs the damage to the cellulose. And so that's my presentation. So here's a little segue. I'm going to really briefly talk about indigo, very, very briefly. So there's a bubbling pot of indigo dye, thanks to Carolyn Talent. And there is some samples drying in the Japanese glade. So to make indigo, we extract indican from indigo-bearing plants. And that's got the, a sugar attached to the indigoyl, indoxyl rather, sorry. We ferment it to remove that sugar group, we get indoxyl. We reduce in an alkaline environment where we form a dimer and form the water-soluble leuco-indigo. And then as that oxidizes, it forms the blue indigo, insoluble, not water-soluble. So when we want to dye something, we put it in an alkaline reducing bath of sodium dithionate typically, and we go from the blue indigo to the leuco water-soluble indigo, and then hang it out in the air. It oxidizes from the oxygen, and we get our beautiful blue as seen. So that's it for me. Take it away, Luke, if I can undo my screen share.
All right, can everybody hear me okay? Cool. All right, can everybody see my screen?
Luke, you're a little faint volume-wise.
Okay, how about now?
Perfect.
All right, and everyone can see my screen?
Yep, looks
Perfect.
good.
All right, so here's just kind of a roadmap of what we're going to cover, because it can get a little confusing. And I gave Nina and Tiarna a little color chart that they should be dropping in the chat. So if anyone wants to download this color chart, you can kind of follow along at home, and it makes things a lot easier. So we're going to first, before we get into the deterioration of the dyes, understand the structure, because we can talk about reaction mechanisms all day, but if we don't understand the structure, it doesn't help us that much. We're going to talk about what makes a dye a dye. So we're going to talk about conjugation, chromophores, auxochromes, and we're going to then look at the redox mechanisms, which are a big reason or a big cause for the deterioration of dyes. And then we're going to look at, put this into kind of a conservation context. So we're going to look at how these materials deteriorate and what we can do to help slow that deterioration, and maybe some ideas for how we can stop that deterioration. So once we understand the actual mechanisms, we can maybe more appropriately approach preserving these objects. So just as a really brief crash course on what a natural dye is. So when we say natural dye, a lot of people prefer to say organic colorants. That's okay too. But so we're just talking about molecules derived from plants and animals that will give another material a color. So before 1856, I think the first dye synthesized, it was, you know, a petrochemical dye. It was an accident. It was discovered 1856. I think it was mauve or something like that. But before that, all the dyes were natural dyes. And so a lot of the dyes that we encounter as conservators pre-1850 are going to be these natural dyes. So it's highly applicable. So whether we're talking about tapestries and textiles, whether we're talking about dyed furniture, marquetry, veneers, silks, wool, any of that stuff would have been dyed with natural dyes. So we're going to stay away from the synthetic stuff, although the mechanisms are actually very similar. So what actually defines a dye? Well, it's basically just a molecule that contains a chromophore and an auxochrome. And the chromophore absorbs light in the visible region of the electromagnetic spectrum. And that's a wavelength of 380 to 740 nanometers. It changes depending on how bad your eyesight is. Like mine, I probably only can see 400 to 700. And we'll dig into the chromophores and auxochromes more in depth. But basically, a chromophore, which chromo color, phores bearer or carrier, it's a conjugated system that absorbs particular wavelengths of light. And at its lambda max, or its maximum wavelength that's absorbed, that will impart a color to a molecule. An auxochrome is just a functional group. So things like hydroxyl groups, OHs, CH3 attached to a group, that's a functional group. Those are attached to chromophores specifically. So if something is a conjugated system that absorbs light in the electromagnetic spectrum, and you attach a functional group to it, that's a chromophore. And so those alter the actual depth or tone of the color. Usually it's what's called a beta chromic shift, so it's becoming darker. And it's also enabling bonding with the substrate. So it's doing two things. The main function is that it's enabling bonding with the substrate, but also just due to its properties, it will darken or lighten the color. Generally, however, though, it darkens things. And when we talk about substrates, dyes bonding to substrates, what we mean is the wood or the cotton, which is cellulose for the most part. Like Chris said, we're going to stay away from lignin. Wools, silks, and cotton and wool have a different bonding type than wool and silk. Wool and silk generally have nitrogenous bonding, although these reaction mechanisms are very similar for those as well. So we're going to focus on cellulose, but it's pretty much the same for wood and silk. So this little chart right here is the one that you should have in the chat box. So I definitely recommend downloading that or screenshotting this and saving it. This is what got me through surviving UV-Vis spectroscopy. But so a molecule that's conjugated may not actually be a chromophore, and it may not be a dye. So if we look at something like benzene, it absorbs light at a wavelength of about 200 nanometers. But as you can see, that's very far, that's deep into the UV region. So that's not going to actually exhibit color because we can only see from 300 to 740. So the molecule has to absorb light within that region, and it has to be able to bond to the substrate. So when we look at a molecule like beta carotene, which we're all familiar with, that's what gives carrots their color. So beta carotene, it's a pretty easy one to remember. We can look at its structure and it's totally aliphatic. It is totally nonpolar. There's no way that this is going to bond strongly with a cellulose substrate. It's just not going to occur because cellulose has quite a number of oxygens and hydroxyl groups, the OHs, as we saw what Chris was showing us. It's not going to bond well to it. So if we look at beta carotene, we can see that it absorbs violet blue light and it's absorbing 455 nanometers. That's the wavelength, the wave that it's absorbing, and it's transmitting orange back to us. So if we look at our chart, we can see that indeed 455 nanometers is right here, where we would expect it to be, where it's absorbing blue and transmitting orange. When we talk about light, remember, light is also energy. It's wavelength, it's also energy. And so we can actually put a number on that. Electron volts, EV, is a really good way to do that. It's similar to like pKa, so that we're not talking about joules, you know, like 10 to the minus 9, those kinds of values. We can put a number like electron volts on this amount of energy that it's absorbing. So when we look at beta carotene, we can look at this system and define a conjugated system. So if I grab my pen here, if we just look at 2 carbons, so let's look at this carbon here and this carbon here, okay? So we're gonna look at that carbon up above. So what that carbon actually has is what are called p orbitals. It has sp2 hybrid orbitals, that's these ones in purple, and then it has empty p orbitals. So if we actually draw the electrons in these, so we all know, so if we look at carbon, we all know that it has 4 valence electrons. So if we draw those in our orbitals here, we have 1 electron in the sp2 orbitals. So here's 1 for each of these carbons. So you'll notice we only have 3 electrons surrounding this. Where's the other electron? Well, it's actually up here in the p orbital. And in that p orbital, we get a pi bond between the 2. And that pi bond is really what enables these molecules to absorb light. Okay, so if we look at a system like beta carotene, we have a large number of those pi bonds present in a molecule like that. So it creates a large band that can absorb light. So if we look at something like benzene, this is what we call the bagel model of color. But so this is a benzene ring where we can see its pi bonds, so it's alternating single and double bonds in those p orbitals. And we can see on the right side the delocalization of the electrons. So that area, that circle that we're looking at on either side, is where light will hit and be absorbed. And it will excite those electrons into an excited state. And that's generally things like, if you hear like pi to pi star transitions, n to pi star transitions, those are electrons becoming excited and jumping up in energy level, okay? So these are our p orbitals, and these are really the big player in color for a lot of these molecules. So if we look again at beta carotene, we can draw p orbitals for each one of those bonds, and we can see that although these bonds don't have a pi bond there, we actually, they don't have a pi bond here that we can see in the stick model. If we actually look at this 3-dimensionally, we'll see that actually there is a bond here between these 2 orbitals. So we can see, if we look at this entire chain, this large band that's going to be absorbing light. And we can't forget this one on the bottom here. And we can actually measure this band. So what does that equal? Well, we can take an instrument, measure this, and see that it absorbs 455 nanometers of light, which correlates to 2.7 electron volts, which we see right here. So what's actually occurring and what's actually producing color? So white light is going to come from a light source. It can be the sun, it can be a light bulb, it can be whatever. It's going to hit the surface, excite the electrons. The electrons are going to jump into, you know, pi star, or they can do a lot of other transitions, and it's more complex than that. But so basically white light is going to hit here. And then what's going to transmit, if we're observing this and we're looking down at this beta carotene, we actually have orange transmitting back to us. So what's occurring is white light is hitting the molecule. It's absorbing the blue light. And what's left over is the energy that corresponds to orange. So we see orange here. So white light's hitting it, absorbing blue, transmitting orange. Okay? So that's really the system that's primarily responsible for color. So if we look at auxochromes then, so how are these actually going to bond to a substrate? It can be colorful, but it's not going to bind, so it doesn't really help us for a dye. So as we said, auxochromes are functional groups, and those groups are just listed up here at the top. We have OH, hydroxyl, amine groups, NH2, aldehydes, CHO, carboxylic acid, CO2H. SCH3, it's the sulfur equivalent of an ether. I always forget if it's a sulfide or not. But anyways, all of those are auxochromes. So they enable bonding to the substrate, and that's generally through hydrogen bonding. They also bond with metal ions, so are called coordinate bonds or dative bonds. And that's going to be important later when we look at mordants. But so when we look at the type of bonding between auxochromes and metals and substrates, we can start to see why mordants are important. They actually boost the bonding ability of the dye, and we'll dig into that. So as an example, if we start on the left and we look at benzene, we can see it's conjugated. Here's our conjugated system, our pi bonds here. That's going to absorb light, but we're not going to be able to see anything because it's absorbing 200 nanometers. We're not going to get a color from that. If we attach a nitro chromophore, and this isn't actually an auxochrome, the nitro group is its own chromophore, so it actually imparts color to the benzene ring. So that's going to give it a very light yellow color. If we attach 3 nitro groups to a benzene ring, we get trinitrobenzene. It's going to impart a really strong yellow color, but still we don't have a hydrogen donor, so it's not going to bond very well with a substrate. If we look on the right side, we can see we've added a hydroxyl group here, that's the OH, so it can now donate a hydrogen and a hydrogen bond to cellulose in a very strong way. And I had a professor that used to say, don't try nitrobenzene at home because it's picric acid, it's explosive. But it does give you a really nice yellow color. So I wouldn't blame you if you did. So we can look at the broader world of dye molecules now that we have a basic understanding of what gives dyes their color. So one of the coolest is cochineal. And I think a lot of us know about cochineal. It comes from a little bug, and it gives a really deep, beautiful red color. And it was really prized, especially from the 18th century on. And with cochineals, generally they have a deep red color, but that can be modified depending on your mordant. So if you actually add calcium hydroxide to it, we can actually shift the color to purple. And so that's a bathochromic shift. It actually shifted it to the right on our little spectrum if you look at your color table. So that's a bathochromic shift from transmitting red to transmitting purple. So carminic acid is based on an anthraquinone chromophore, and that's the core of this molecule. And it requires a mordant to bond to a substrate. So the potassium alum acts as a mordant and aids in bonding to the substrate. So if we look at this aluminum here, that's from the alum and potassium alum, it's acting as a coordination ion, or it creates this coordination complex that is connecting these 2 carminic acid molecules, and where this OH or this H2O could actually be cellulose. It could actually be bonding to cellulose with either one of these bonds here. So it has 2 sites available where it could bond with your substrate. So metal mordants like aluminum, and other common ones are iron and copper, we're going to form these coordination complexes. Some of them are octahedral, like this aluminum one, and it's going to complex the dye, the substrate, and the ion. So it's going to create a strong bond. And those bonds are called dative bonds or coordinate covalent bonds. And they're a little complex, but they're basically a covalent bond, and we can think of them that way. And as we know, hydrogen bonds are about 1/10 of the strength of a covalent bond. So if we have a dative bond present, the bond of the dye to the substrate is 10 times stronger than with just a hydroxyl group alone. So just as this molecule alone, if you were trying to rely on this OH bond to bond to a cellulose substrate, it might bond a little bit, it might be an okay bond. But if you add this aluminum to it, the bond to the substrate between the dye and the substrate is actually 10 times stronger because of those dative coordinate covalent bonds. And so that's really what's responsible for the extra bonding strength for metals. It's that dative bond that we're looking at. So another really interesting dye and a really ancient dye comes from Weld. And luteolin and apigenin are the main coloring chromophores, or the main coloring molecules that give Weld dyes their color, that yellow color that they have. They're a flavone, or they belong to the class of flavonoids, and those are just metabolite compounds. They're in, I think, in all plants. And These dyes are water soluble, and we think about them existing in a biological system, so it probably makes sense that they should be water soluble, like a lot of these dyes tend to be. And we see that it actually would require a mordant to bond to a substrate. And this is another case where the use of a mordant will actually shift the color depending on which one you use. So tin chloride and potassium alum are going to give you different shades of yellow, but a mordant that's based on iron sulfate or copper sulfate, the iron sulfate is actually going to produce an olive green color, whereas the copper sulfate is going to produce a yellow green color. And that's because these metal ions, like an iron or a copper, are actually chromophores themselves when they're in that octahedral configuration. So it's not just an oxochrome, it's not just a dative bond, but an iron atom, for example, coordinating these is actually going to be its own chromophore. So it's actually going to shift the color of this. So if you look at your chart, you can see the iron sulfate is actually enabling the entire dye complex to absorb a wavelength that's 200 nanometers longer than just luteolin or apigenin on their own. And so it shifts it by 0.9 electron volts, which gives you that green color. So the iron or copper is actually acting both as a chromophore and oxochrome, and it's also acting to bind the substrate in the dye complex. So it's doing a lot of different things. And iron chemistry is complex. So if iron chemistry is confusing to you, don't worry, you're in good company. It's confusing to everybody. And we're going to dig into it more a little later. So if we look at something like this indigo, we can see that it has a nice chromophore, a nice conjugated system here. It's an alpha beta diunsaturated ketone at the core of this thing. This is actually the chromophore here. These benzene rings don't really actually play much of a part in indigo's color. But disrupting the chromophore or the oxochrome is going to lead to fading. So if we were to break this bond here in the center, it would cause this material to fade because we've disrupted the conjugation. If we just have this now, these carbons here would no longer be sp2 hybridized. They would no longer have those pi orbitals. So those would just have hydrogens attached to them, and it would just be a regular planar system like that. It wouldn't have those nice p orbitals over the top. So it wouldn't be capable of pi bonding. So that's what breaking a double bond in a conjugated system will do. It will lead to fading. Also, if we strip off these hydrogens from the indigo, that'll also lead to fading. It's going to affect the way the dye bonds to the substrate. It can cause the indigo to wash out more easily, but it also changes the polarity of the molecule. It changes the dipole moment of this whole system. And so when it does that, it also leads to fading, and we're going to look at that more a little later. That type of fading is generally called a hypsochromic shift, so it's a lightening. So we're going from a deep indigo blue to a light blue, or maybe even we're mixing yellow and blue, so indigos can go green. I think a lot of us have probably seen that before. And usually the culprit for this is photooxidation. That's generally what's causing these types of reactions. So there are a lot of contributing factors to photooxidation. The big ones, though, are light, oxygen, atmospheric pollutants, and ambient humidity. Those are our big ones. And pollutants can include just things like dust or volatile organic compounds. That's those VOCs. The two big ones, though, it's light and oxygen. Those are our main culprits. The dust, which lands on objects constantly, we're constantly battling dust, whether it's in a private collection or a museum collection. That can contain proteins, halides, salts, skin cells, combustion engine products, all kinds of stuff that's going to settle on a surface and act as a reagent in some of these reactions. So each one of those different factors can cause rearrangements within the molecule. It can break bonds, and it will generally lead to a characteristic deterioration pattern for each molecule. So while some random bond breaking does occur and random rearrangements can occur, it usually follows a particular pattern just due to the inherent structure of the dye molecule. So if we look at this one, this can be kind of an intimidating slide, but it's not that bad. We'll all make it. We'll all get through this and it'll be okay. So if we look at this, just in the presence of light, which is HV or H-nu, we have O2, which is atmospheric oxygen, we have light. And that causes an excitation of both the dye molecule, so light is hitting this, as well as excitation of the oxygen. And so what occurs here is what's called radical abstraction of a hydrogen. And this is a really common reaction. This happens all the time. It's probably happening in your house right now. So what occurs is that one of the electrons in the covalent bond between the nitrogen and the hydrogen, one electron from hydrogen goes and bonds with oxygen. The other electron stays on nitrogen, and that creates a radical. And we usually symbolize that with just a little dot. And that's that purple dot here in step 2. So we see the lone pair of electrons on nitrogen in green, and we see the radical in purple here. This radical can most easily react next with the pi bond it's next to. So the pi bond itself is actually the p orbitals that contain the pi electrons. That's actually an easier bond to break than the sigma bond. And so it's going to attack that pi bond, and we're going to start disrupting that chromophore almost immediately. So it's going to take that red electron from the pi bond and form this double bond that we see here. Okay, so now we've formed a double bond here. And so this reaction can stop right here, or it can continue over here and actually repeat the exact same process on the right side of the molecule. So we could have radical abstraction of hydrogen here, and then we can have this new pi bond form between carbon and nitrogen. And that would result in this molecule over here, which is dihydroindigo. And that has a kind of a yellow-orange color. And so this is a really common degradation pathway for indigo. And so this yellow-orange color mixed in with other blue molecules, well, mixing yellow and blue gives us green. And so that can actually be responsible for some of the indigo's color shift and some of its fading. And so this could actually just stop right here. If all of the indigo molecules shift to dihydroindigo, well, now you have yellow instead of what was once blue. So we can actually end this here if we wanted and call it a day. But we could also introduce a couple water molecules. And we can actually completely destroy this molecule through another reaction. And we can actually cleave this central sigma bond right here. So where are these water molecules coming from? Ambient humidity. It's just water vapor. It's just in the air. It's around it all the time. So what can occur when we look at this dihydroindigo molecule, we see these green electrons on this nitrogen. Let me switch my pen color here so we can look at this more easily. This nitrogen, the pi bond here at this carbon broke and flipped over to nitrogen. So the nitrogen actually went from having its lone pair in the pi bond where it had 2 electrons here. So this is step 1. This is what the nitrogen looked like. In step 2, because that pi bond broke, the nitrogen, it still has p orbitals, right? It still has the pi bond, but it actually only has 1 electron in it. And its lone pair is actually hanging out outside of the molecule in a separate p orbital. So we could actually draw those electrons out here. That lone pair can be out here. We can actually see why those would be a little more reactive and why those might grab a hydrogen from a water molecule. This is also what was partially responsible for the color shift. This changes the polarizability of the molecule. We go from having 2 electrons participating in the aromaticity of this pentene ring to 1 electron participating in that ring. So it actually changes the polarizability there. But so we can see this pi bond, or I'm sorry, these lone pair of electrons can attack a hydrogen from a water molecule. When it does that, it transfers electrons to the more electronegative oxygen. This isn't a radical reaction. This is just a regular attack from a nucleophile attacking an electrophile. If we look over here in step 5, we see that O-, that hydroxide ion over here that we created in step 4. So we have this NH that now has a positive charge on it because nitrogen has 4 bonds. We have the OH that we produced actually attacking that pi bond. And by doing so, this is actually a really energetically favorable attack here, because when this O- attacks this pi bond, it kicks 1 electron back to the positive nitrogen and neutralizes its positive charge. And at the same time, the oxygen donates an electron to this carbon that's right here, and it actually neutralizes its negative charge. So you're actually neutralizing two charges at once with this attack. So it's very energetically favorable. So in step 6, can anybody spot the big difference between 6 and 4 and 1? If we look at 1, we actually have pi bonds here. The chromophore itself hasn't been destroyed yet. Those are still there. And these form Indigo's alpha beta dye unsaturated ketone. When we get to step 6, notice there's no pi bond here anymore. It's only sigma bonds. So the conjugated system has actually been broken at this point. So here you would have extremely significant fading. So once you get to step 6, you've probably shifted from a yellow-orange to an extremely faint yellow. So at this point, this chromophore has actually been destroyed. It's still going to absorb sunlight, but not very much. We can continue again with a radical oxygen interaction here. So we should have a little light right there. But so we can have attack from atmospheric oxygen, abstracting the hydrogen here, which is then going to kick an electron back onto this oxygen, create an oxygen radical here, which can then sever or cleave this pi bond. So we can see the two blue sigma bond electrons here. Well, that oxygen radical can absolutely attack that. And then we look over here in step 9, we have a double bond here. So we actually have a ketone right here. So when we look at this carbon here and here, what have we done? We've actually oxidized it, and we've increased its oxidation number by 2. And at this point, the Fisetin, it can be an extremely dark yellow-orange color, or it can also even be not colored at all. If we look at actually the energy and wavelength, we're going from a regular indigo molecule absorbing 613 nanometers to the dihydro indigo absorbing 480 nanometers. That's still in the visible spectrum. When we get down to Fisetin, that's actually at about 370 nanometers. So it's right on the edge of that 380 nanometer cutoff point. And I put the deltas in here. So delta means a change. So that we have our delta lambda and delta E for energy. So we can see that the wavelength from 1 to 4, from indigo to dihydro indigo, the difference in wavelength is actually 133 nanometers. It's not that big of a change, but it produces a large change in color, because we always have to remember that the visible portion of the spectrum is very small. So small interactions and small changes have big consequences. So we can also look at the change in energy. The actual energy difference is from 2.02 electron volts absorbed to 2.58 electron volts absorbed. So the actual difference in energy being absorbed by this compound, the difference is only 0.56 electron volts. That's all it's absorbing. It's only absorbing 0.56 more. So it's really not that big of a change, but it has, again, large consequences. Okay, so we can look at a couple different pathways really quickly. So we looked at one radical pathway, and we spent a while on that one because that's kind of a template pattern for radical abstraction and radical reactions in these organic molecules. So this additional pathway, if we look here, we can see ozonolysis occurring in A. So this immediately destroys the chromophore. In B, if we start from dihydro indigo and start with a radical oxygen reaction instead of a water reaction, we can also destroy the chromophore from that step. And then in C, if we actually have a nucleophilic attack of water, if this is really getting bombarded with light, this can occur, where water is going to attack the carbonyl carbon of the ketone and add directly there. And what will actually result in a diol, two hydroxyl groups right here. And again, you'll notice that the chromophore has been destroyed instantly. And so this is just to illustrate that while the radical pathway is probably the most common pathway, there are a lot of potential reactions that could be occurring to disrupt the chromophore. But that's the fundamental. The chromophores and the auxochromes are being destroyed, removed, altered in some way. So if we look at a practical case study, this is a table by Jean-Francois Oeben that's at the Getty Museum. And we look at this tabletop, this Marquetry tabletop, and we notice that there are flowers here, but the stems and leaves are all blackened. So Arlen and his group at the Getty did a study on this. They found that the main dye component was probably iron sulfate and yellow dye from young Fustic. And it has two main coloring components, or two main molecules, which are Fisetin and Fustin. And those two molecules are very similar to the Weld molecules we looked at earlier, those same yellow molecules that also produce an olive green color when you combine them with iron sulfate. So if we look here, they publish these amazing photos, but we can see where all of the dyes are labeled here in this photo. And if we look at the Fisetin, the Fustin, and luteolin, we can actually see how similar those flavo and chromophores are. Really, it's just, again, a difference of the position of hydroxyl groups, or whether maybe there's an extra hydroxyl group, but all of these produce a yellow color. So all of these are giving us yellow. So this is what that table should, or probably looked like, or looked something close to this when it was made. So the iron sulfate and yellow dye should have given us a nice green color, which makes a lot more sense for leaves and stems. And generally with marquetry, it tends to photodegrade quickly. So when you see this in a museum setting, you often see that it has browned. And here you can see just how vibrant and really phenomenal this tabletop is. It's just absolutely incredible. So we can look at another type of degradation, another deterioration pathway. Up here in the top left, that is the iron sulfate that would be present in an aqueous dye bath being used as a mordant. So this is going to be iron with a bunch of water around it, essentially. And remember, again, we said earlier that when iron is in that octahedral configuration, it acts as a chromophore. And so this is the octahedral configuration of iron. And this is what is acting to augment the yellow of the Fisetin and the Fustin and give us the green. It adds that 200 nanometers wavelength absorbed. So we go from yellow to green when we make this compound. And here we actually have it bound to a cellulose molecule. So we can see that dative bond between the iron and the cellulose, providing a bond to the substrate that's 10 times stronger than just a hydrogen bond from a hydroxyl. So we can see how that mordant is functioning here. And we can also see the sulfate group attached with a dative bond to the iron, and the iron is in its 2+ oxidation state. So I put this molecule here just plain as is without anything going on, so you could kind of see what that octahedral configuration looks like. So the first step in deterioration of something like this could be an attack of something like chlorine. It could be oxygen, it could be water, it could be a nitro group, or it could be nitrogen dioxide, carbon dioxide. It could be a lot of different things performing this attack. I just picked Cl because it was small and we can write it easily and keep track of it a little better. But this reaction can actually occur with a number of different contaminants. So these could establish themselves on the surface of an object as dust. It could also be from volatile organic compounds. Another thing in a museum setting, we increase the levels of CO2 generally because we're in a crowded room breathing heavily. That'll increase CO2. And this kind of reaction can actually occur with as little as 0.1% of oxygen in the atmosphere. We generally have about 20% oxygen in the atmosphere. So there are a lot of things that can cause this reaction to occur. So we're going to pick chlorine. So we're going to do another radical reaction here. So we have one electron from iron. We have one electron from chlorine. So remember, light is bombarding this and exciting everything. So this is from a light bulb or the sun. And remember, a lot of these objects have only been in museums since maybe, if we're lucky, the late 18th century. A lot of these have probably had a long life in uncontrolled environments. So it's being bombarded. And so that initiates this radical reaction. So this is our initiation step. So we have one electron from iron, one electron from chlorine. Once this attack occurs, and it's kind of a coordinated reaction, it happens kind of in concert. At the same time, iron is going to lose its bond to the sulfate group. That is the most energetically favorable bond to lose, essentially, because H2SO4 is going to be formed after reaction with atmospheric water, and that's quite a stable molecule, which will then come back to play a role later. So here in our next step, we can see that we added a chlorine to the molecule. So before we had a sulfate group there, and that is what we call, I have to look at my notes, but I think it's a strongly oxidizing ligand. Let me double check. Strong field ligand. So we had sulfate there, a strong field ligand. A chlorine group is actually what's called a weak field ligand. And when we add chlorine, we actually cause a bathochromic shift to the right. It also tends to produce, when adding chlorine, more of a brown tone, a brown-black tone. So I think you can all probably guess where I'm getting at. So we're adding chlorine. We had another chlorine radical produced during that initiation step. So notice that when the H2 or the HSO4 left, it took 2 electrons with it. So it lost electrons. So it was oxidized. And so it went from +2 to +3. So this iron went from +2 to +3. And so now what's going to occur, this chlorine is going to perform a radical attack on this iron, and it's going to give its electron to the iron. It's going to then lose 1 electron to the OH bond of the cellulose, and it's going to break there. That's the most energetically favorable bond to break. So it's going to actually go from +3, and we're going to reduce it because we donated an electron, and we're going to reduce that back to Fe2+. So here in our step 4, we've actually added 2 chlorine molecules to this, which is going to cause a strong bathochromic shift. And we're going to get a really deep, dark brown, black color from what was once green. And so this is really where iron chemistry becomes important. And I think a lot of us tend to finish organic chemistry too, and then go out and celebrate. And we forget that inorganic chemistry is out there kind of looming. And iron chemistry in particular is quite complex. So if you don't understand this kind of splitting, that's okay. But what occurs here when iron is in this octahedral form, it actually has access to what's called, iron has access to what are called D-orbitals. And so this is kind of the orbital configuration of iron when it's in the octahedral form. Notice that the energy gap here is actually less than it is over here. So over here, we have these CN groups, which are strong field ligands. And over here, we have weak field ligands. So these ones are weak. So if we replace strong field ligands in a molecule like this here, in this octahedral coordination, we're actually going to cause bathochromic shifts towards darker colors. And that's really the important part. So the d orbital splits. When you add chlorines and atoms like that, which another example is one like bromine or fluorine, when you add those to a molecule like this, it actually decreases the energy gap between the HOMO and the LUMO, the highest occupied molecular orbital and the lowest unoccupied molecular orbital. So that energy gap decreases, and the wavelength absorbed increases because energy and wavelength have an inverse relationship. So an increase of wavelength is what? A bathochromic shift. It shifts to the right and you get a darker color. So this is one possibility for the fading from that brilliant olive green color to that quite drab brown black color in that Oeben marquetry. So we can see how important it is to protect these objects, whether through appropriate surface coatings or through appropriate environmental controls, good maintenance, getting it in there and actually dusting every now and then. That's a good way of controlling this kind of stuff. So we can see, how easily these reactions can occur and with how many different types of reagents it can occur with. So how many different types of compounds can actually facilitate these reactions. And it actually really doesn't take that much energy to catalyze these. It really doesn't take much energy from light to cause these reactions to move forward. So I think we hit most of our objectives. So we talked about the structure and the properties of natural dyes. We looked at their functions and the properties and structures of conjugated systems, chromophores, auxochromes. Talked about redox, which were those radical reactions. Those are the redox mechanisms that were those reduction and oxidation. And we talked a little bit about the importance of surface coatings and environmental controls. So basically the big takeaway is that photooxidation is insidious. It's happening all the time. And if we can understand why these reactions occur a little better, maybe we can do a little bit better job of preventing them from occurring in the first place through proper environmental controls and proper maintenance of our surface coatings. So at some point in the future, we'll talk about surface coatings in a lecture. But if you have an appropriate surface coating on a painting, a piece of furniture, a metal, whatever, that's actually going to photooxidize and sacrifice itself. So that's photooxidizing instead of your substrate, which is what we want to save. So that's simple, right?
So that was a ton of content. And now we're going to have some fun. Luke is going to share a poll with you that we devised, and please be honest in your answers. This poll is to help determine your conservation science personality type, a la BuzzFeed quiz, but it is also a way for us to gauge kind of what we're doing, how we're doing, how the content is. So if you would take the poll, then after we finish the poll, I will share with you the conservation personality types.
And the responses are completely anonymous. So
yeah,
none
they're
of us can
anonymous.
see.
All we'll see is the percentages. We won't see people's names.
Right. Another thing too, this was recorded. So I know that's a lot of information delivered quickly, but it can be revisited as many times as you would like, as long as you're not sick of it. If you're sick of it, don't watch it again, it's fine. Okay, can everybody see the poll?
And I believe you just click on the answer that best fits what you're doing.
Okay,
well, Nia manages the poll. I'm gonna go.
It's actually not working for me. Is that because I'm a co-host or?
Yeah.
Okay, good. Whew.
Don't get to.
Can someone confirm it's working for them? Oh, someone's asking, where is the poll? It should be showing up on your screen.
Yeah, it should be there. We have some
people are answering
voting.
it.
Oh, good. I see it now.
It should show up. So if you have questions for the lectures, you can start putting them in the chat, or you can wait, and in a couple minutes we'll come back and we'll start our Q&A discussion.
So once, if you could just shoot me if you know how to do the thumbs up on your box, please do so when you finish the poll. It should be, if you click on the upper right corner of your box, you should be able to, no, where is it?
Some people have a reactions button, Nina. Is that where you want people
Yeah.
to do that?
Oh yes, if you have a reactions button, it should be on the bottom. Click that, and you should be able to do a thumbs up like that when you finish the poll. So on the bottom of your screen, all the way on the right, there's a smiley face that says reactions. I'm gonna put my
Thumbs up
costume.
only lasts for a few seconds, so it won't stay up.
Okay.
Hey, Arlen, thanks for sharing that great image and your research on the table.
Oh yes, thank you so much.
Well, now I finally understand what was going on.
Maybe. Denise, yes, denim jeans are dyed with indigo, and this is a part of why they fade so much when you wash them.
I was very glad to hear Luke say that iron chemistry is complicated, and I don't feel quite so bad for not understanding it at all.
I think everyone is in that boat. Everyone feels like they should understand it, but it's generally not covered in most general curriculums. So when you start bringing up metals, people just kind of freeze up and grimace. But really it's complex for everyone. And the d-orbital splitting is far more complex than that. It will involve the spin states of the oxygens, electrons. It'll also involve, bonding, anti-bonding orbitals, constructive and destructive bonding, and that kind of stuff. It will also highly involve the types of ligands bonded to the iron atom. And so that's kind of what we were talking about, the strong field and weak field ligands. So depending on what's bonded to that iron molecule, it will drastically change the color. It's really fascinating when you get into it. That's one of the things I love about inorganic chemistry, although it is complicated enough to make you drink.
It's used a lot in alternative process printing from photographs?
Yeah, I mean, iron is used in, I mean, it's like the fourth most common element in the Earth's crust. So, I mean, well, we don't have access to a ton of it. Most of it's in the core. But, I mean, it's used in so many different things. And I think as conservators, it kind of does us a disservice to not understand some of the metal chemistry, or at least some of the basics, because so many of the objects we work with have metals incorporated into them, even though we consider them as organic materials. Metals play a huge part in their deterioration processes. Oh, I think Nina started sharing her screen.
Trying to. Okay, so you guys can keep talking, but
Oh no, this is way more important.
Okay, I thought I would do the. Oh, but now that I made it so big, I can't figure, how do I do that? Okay, so if you answered 1 to most of the questions, you are a super geek. This is you in your lab. You are a scientist or a conservation scientist. You have an advanced degree. The poll's now over. You don't perform a lot of treatments. You may or may not be enjoying these calls, and you may be one of the few people. Luke was horrified after the last call because he called the protein by the wrong name, but no one else noticed. But maybe you did if you are a super geek. And other super geeks are Robert Feller, Stephen Hawking, and Walter White. Please go to the next slide. Okay, why is it not doing that? Wait a minute.
Might need to click it. I can also share it if we have to.
Why is it not advancing to the next? There we go. Sorry. So if you answered mostly 2, you are a nerdy geek. You probably majored in chemistry during an undergraduate work. You may have an advanced degree as well, but you still treat art. In conservation school, you helped your classmates with chemistry and could not understand why some people did not know a spectrometer from a photometer. You have more than one type of stir bar, like Luke, and actually know the difference between pKa and pH and think that it matters. You are loving these calls because you are surrounded by your people, and other nerdy geeks are Chris, Luke, and Tierna. If you answered mostly 3, you're an artsy nerd. You also have some lions and skulls in your studio. You struggled through just enough chemistry to get into conservation school. For you, the best part of organic chemistry was the cool model set that you never actually got to use. Some of you may have forgotten almost all the chemistry you crammed into your brain the day after the exam. That was me. Some of you may have rediscovered how useful it can be as part of your conservation practice. You may be loving most of these calls, but sometimes you wonder how the hell these guys made all those drawings of molecules rotate. Other artsy nerds are myself and Craig Deller, and I think most conservators out there. If you answered mostly 4, you're a newbie. This may be your introduction to the dark arts of chemistry, and you feel like this guy just overwhelmed with life in general. You forgot everything from high school chemistry, and you're thrilled to have this fun forum to discuss things you may have heard of before. Please know that we are here for you and want you to feel welcome and supported on these Zoom calls. Remember, there are no dumb questions, and other newbies are out there, and many of them are on this Zoom. So. Let me go stop screen sharing.
So some of us did make molecules.
Yeah. Did you guys see did the screen share finally work?
Yeah, I shared it.
Okay, that's why.
Companies work for Bob Feller too. I
Yeah.
thought that was a pretty nice comparison there.
Okay, so we have one other thing that we wanted to talk that Tierna is going to introduce, and I am going to share if I can find my.
If you want, Nina, I could share the screen. I've pulled up the green slide.
Okay, good, because I don't know what happened to mine.
Sorry, there we go.
Looks good.
Nina, would you like to take it away or shall I?
Okay, so, well, we've had some feedback that people weren't super happy with our name. And we really want to have a name that we based it on the Drunk History TV show. And we want to have a name that emphasizes a fun, casual atmosphere. reflects the rigor of our scientific discussion, attracts conservators, scientists, and conservation scientists. And we thought when we sort of started the name that it was okay, but we sort of have gotten feedback and we don't feel great about it anymore. So I think Tierna had some other things to say about it as well. So.
Sure. So we're struggling, so we want to ask you all for help with this. You know, if we go with something like cocktails for conservators, we're still referring to alcohol. Science for conservators might be a little too dry and boring. Conversations. I feel like so many of us actually stumble over that word the first time around. Conversations with conservators. It's a mouthful. It's also a bit too vague. And so, you know, again, just to reiterate what we had up there, you know, we're really excited about this being a forum for constructive exchange. We had such a good time last time, had great feedback. So we want going forward to invite other people to present here in this forum, conservators, scientists, conservation scientists. So we welcome your feedback, and you know, if you want to submit ideas tonight, you're welcome to, and if you can do it over email to any of us, we'd really appreciate it.
We've had some really good suggestions already. One was science for all kinds of conservators, ALKYNES. I see the nerds. The nerds are all nodding their heads.
I like conservation alchemy. That's good too.
And then I think I'll share maybe our next event now in case people have to get going, and then we can start our Q&A. So here's the last screen share for the evening. So this is our next talk, which I am extremely excited about. One of my favorite people and scientists on the planet. We are all extremely lucky that he has agreed to show up and talk to us. Dr. Greg Hodgins, he's in the Department of Physics at the University of Arizona. He's the director of the U of A Accelerator Mass Spectrometry Laboratory, a phenomenal organic chemist, and extremely skilled in radiocarbon dating, extremely knowledgeable. So he's going to do for us a talk on radiocarbon dating for conservators. So Greg has a Bachelor's of Science in Biochemistry and Molecular Biology from the University of Toronto, a Master's of Science in Biochemistry and Molecular Biology from Cornell, and a doctorate in Archaeological Science from the University of Oxford, where he worked on the characterization of binding media and Renaissance oil paintings. So not only is he an amazing scientist, but he's also an art nerd like us. So we can pester him with all kinds of art and science questions. So he works here in the radiocarbon dating lab. He's assisted me multiple times with radiocarbon dating, and we are all in for a huge treat. And so that's going to be on December 4th, because we don't want to have an event on Thanksgiving weekend. So make sure to mark your calendars for that and do not miss it. It's going to be incredible.
And if we can, we'll post some references to articles he's written. Of course, because of copyright issues and whatnot, we may not be able to circulate articles, but we'll certainly provide some information on our Facebook Modular Cleaning Program page in advance.
Mm-hmm. Yeah, definitely. And there's a lot of really interesting material that he's published that is available for free on, you know, like academia, EDU, and stuff like that. If you want to check out some of that, and even some stuff on analyzing paintings, dating paintings from radiocarbon samples from substrate, like a cellulose canvas, stuff like that. Really interesting stuff.
He was also one of the early people who did work on using antibodies to study binding media in art.
Oh,
Yeah, we're very lucky he's agreed to talk with us. I'm keeping his bio short, and I don't want to embarrass him, but he's done a lot of amazing work.
So going back to the Q&As, I'm just going to sift through the chat chronologically and ask some of the questions. If you've asked the question and you want to unmute yourself and talk more, please do so. The first question was from James Churchill. With the silver and aluminum through hydrogen sulfide, what happens to the sulfur? I couldn't see the reaction.
the sulfur ends up on the aluminum. So you get aluminum sulfide. The electrons move one way through the wire and the sulfur ions diffuse through the electrolyte and end up on the aluminum.
So what do you think is happening? This is from Denise Stockman-Wallace. What do you think is happening in paper if you alternatively apply hydrogen peroxide and sodium borohydrate? This has been shown to lighten oil stains better than either alone.
Fascinating, no clue, no idea myself. Interesting that it would be working on oil stains.
Well, so if you combine the two, sodium NaBH4 and H2O2, you have potential for attack of pi bonds and conjugated bonds that will result in addition of hydrogen and an alcohol to the pi bond. So that could be one thing. So the pi bond breaks, you add hydrogen to the most substituted. It is the opposite of Markovnikov addition. And so you add a hydrogen to the least substituted. No, I always do that backwards. You add hydrogen to the most substituted carbon, BH2 to the least substituted. Hydrogen peroxide comes in, replaces the BH2. So you've reduced a pi bond to an H and an OH. So you also have attack at the carbonyl carbon of the ketone. So you can also, with that system, the NaBH4, attack that ketone and reduce that to an OH oxygen group. And the same thing would occur with an aldehyde. Aldehydes are more reactive than ketones anyway, so it's actually very favorable reaction. So I imagine the two together, that's a pretty standard system, sodium borohydride and hydrogen peroxide for adding alcohols to pi bonds. That's my guess.
I'm just looking for more.
I can jump in there, Nina. Early on, we had one. I think Chris is for you, and you were talking about silver. Question about with the silver to aluminum through hydrogen sulfide, what happens to the sulfur? I couldn't see the reaction.
We did that one already, but that's where the sulfide ends up on the aluminum.
Sorry about that.
From a paper person to textiles people, I dabble in natural dyes, but I'm concerned about the effects of mordants on textile substrates. Do aluminum and iron degrade cotton and linen fabric?
Yes, they do. And we looked at part of that in the last reaction mechanism. Iron is an extremely good catalyst for a lot of different reactions. And we saw that its oxidation state went from +2 to +3 back to +2. And when we are adding halogens or oxygen and other things like that, we increase the probability of producing peroxide radicals. So things like H2O2 can be produced, superoxides can be produced, peroxides can be produced through iron acting as a catalyst. And the peroxide will then attack those cellulose bonds, those 1,4 bonds that Chris showed earlier, where you have an oxygen bridging the two molecules together. Those sites are very prone to attack by radicals, and it's what we call in wood conservation unzipping the cellulose chain. So it's very common, and so that will happen in textiles and wood alike. And it's also analogous to the way brown rot and other fungi deteriorate wood. It's through a peroxide mechanism. If you've all seen that cubical brown rot that occurs in wood, that's through a peroxide deterioration mechanism.
Yeah. And we see that same kind of degradation with foxing caused by iron.
Mm-hmm. Another thing too is that if sulfates are used as the mordant, and I spoke with Arlen about this really briefly, some H2SO4 will be produced, some acetic acid will be produced. So then you have regular hydrolysis reactions occurring. It can protonate oxygens, which then causes substitution reactions or nucleophilic addition attacks, stuff like that. So iron is basically a catalyst that will catalyze a large number of reactions. And the more of it you have, the more likely it'll occur. So for example, in the Oeben tables, perhaps 10% of the dye bath consisted of, or there was a 10% solution of iron sulfate in the dye bath. So there was a large amount of iron sulfate in that material. And we saw that it became black over time. And also the cellulose itself became almost charred or burned, it seemed like, and very embrittled, which is a side effect of peroxides and acids attacking cellulose.
So there's some questions related to the fading of indigo. Someone asks about how often does indigo fade? She hadn't seen any faded indigo. It was really interesting. I happened to do a symposium this week on wall paintings, and for some reason, one of the early 19th century wall painters liked to use indigo in his backgrounds, and some of them had faded from blue to kind of a yellow-green color, so I thought it was interesting. Another person asks, on behalf of an artist, is there a problem with using the already faded indigo because the artist likes the yellow-green color of the indigo?
Well, yeah, sure. You know, so we saw at step 4 in the mechanism, the continued deterioration of the indigo chromophore to step 6, where we were actually destroying the chromophore and eventually ending up with a bright orange or non-colored Fisetin at the end, or stopping at step 6, where the chromophore is destroyed and you get severe deterioration. I mean, it depends on what the binder is. It depends on what the surface coating is. That makes it a huge difference. If you pour epoxy over the top of it with a bunch of UV blockers, it'd probably be fine. So it's really just situational, but there's no reason it wouldn't continue deteriorating like any other indigo molecule, given enough light and moisture and heat. You can do a test, take a sample, put it on a board, set it outside for a couple weeks and let it get sunlight and see what happens. There's a huge amount of energy in natural sunlight. There's also quite a bit of energy that comes from a lot of lights just in your house or even in some museums. So that catalyzes those reactions. So it will occur. It's just about, you know, the length of time it occurs over. If you have a textile from the 15th century that was dyed with indigo, it's very likely going to be quite faded. So if you look at some of those, you're going to see the fading there. So is it going to fade next week? Probably not, but a few years from now, probably.
So someone else asks about a commentary or good sources to read regarding iron chemistry involved in the making of iron gall ink.
That's interesting. Oh, Chris, you can go ahead first.
No, it's a really difficult topic. Go ahead.
Yeah, so another thing that I thought was really clever about the poster and chapter published by Arlen and his team was they made the connection between the deterioration of iron gall ink and the dye that was in that iron sulfate young fustic dye complex. They connected it to the condensed tannins, which is actually a really similar structure to what we looked at. And so the deterioration mechanisms are probably similar. Where you can go to look at that specifically, there is a website that's called like the Iron Gall Ink Project or it's something like that. It's on, you can just look up Iron Gall Ink Deterioration and it'll pop right up. What you can also do is go to our modular cleaning group on Facebook, and there is a file with links to lectures, and there are 2 semesters worth of inorganic chemistry videos linked there where you can look at this, because it's not really as simple as I'm going to understand iron. You kind of have to understand all of inorganic chemistry first. You have to understand molecular orbital theory quite well for this kind of stuff. So you can go watch those videos, and that's a really good way to get into this topic. And it's one of those subjects where every time you watch a video, it'll expand what you know by a lot, and you'll start to be able to make a lot more connections.
So Debbie Ormond, who has an incredibly distracting costume on, because I know that's not what she looks like, is Luke's color chart related to 19th century color theory as explained by Chevreul and Blanc? I noticed the complementary colors relate to colors absorbed and colors transmitted.
Definitely not related to that. It's related to my UV Viz spec book for my class. But it's a pretty general way of looking at colors. Another thing is that the boundaries are kind of smeared. Those aren't absolute nanometer and electron boundaries between those colors and stuff. So there is a gradient where those occur. But no, it's definitely not based on that, but it is a pretty good roadmap for this kind of stuff and understanding where things are shifting and what's occurring.
So Marika, our lovely colleague from Australia, has posted the irongallinc.org link in the chat, so please check that out. And then Patrice Lejeune asked, will every kind of light create damage over time?
Over time, yeah. Some light is less damaging than others. So UV light is more damaging than white light. White light's more damaging generally than infrared, although that depends on how close infrared light is and how much heat is being generated by it. But yeah, I mean, light is always an issue whenever we're dealing with deterioration.
So that's it for the questions in the chat. I suppose if anyone else has a question, or if I did miss one, just go ahead and unmute yourself and talk. Otherwise, it's 9:45 on the East Coast. So some of you may be getting ready for bed.